Welcome to Unit 1, Lecture C. We're going to be talking about naming compounds. Some teachers wait and do naming of compounds later in the year. I like to start right at the very beginning because for some of you, naming compounds is going to be a little more difficult. And for some of you, naming compounds is just going to make sense right from the very beginning. So we're going to start early, and by the time we get midway through the year, hopefully it clicks for everyone. Just quick review, the symbols that we use in chemistry are a shorthand. They are not based on the substances or the element's English name. They're based on the Latin names that all of the elements were first called by when scientists first started doing chemistry. And so again, use reference table S until you get used to them. And even on your final exam, even if you think you know what the symbols are, it doesn't hurt to double check just in case. They gave you the names and the symbols here on table S, so use them. If you have to name a compound, make sure you're spelling it correctly. The spellings are all listed here for you, so I expect you to spell them right. And all of the symbols are here, and we talked about this before. Capital for the first one, lowercase for the second, and don't use just very big letters and little letters. Use proper capitals and lowercase. It'll become important. If you want to know where they are on the periodic table, then their atomic number becomes helpful because the periodic table lists them in order of increasing atomic number. The chemical formulas then that we use for compounds are going to be combinations of these symbols and subscript numbers. So sometimes people aren't sure what I mean by subscript. When you are writing and you write a number or a letter that's lower than the normal line, so here's the normal line of writing. When I put a 2 that's down here as a subscript, instead of a big 2 that's the same height and size as the hydrogen, this is what I mean by subscript. So water, H2O, it gets written with a capital H, a subscript 2, a capital O. These little subscripts indicate how many of each thing there are, and they always apply to what's right in front of them. So this 2 only applies to that hydrogen, so that means water is made of 2 hydrogens and 1 oxygen, because just like math, if we don't write a number, the number there is 1. It's just understood to be 1. The number goes to the next capital letter. If there happens to be parentheses in a compound, so if I have magnesium hydroxide, they write that as Mg parentheses OH N parentheses 2. Just like in math class, this 2 is going to apply throughout the parentheses, and the parentheses only. What this is really saying is that I have 1 piece of magnesium and 2 of these hydroxide units, 2 of these OH units. And the parentheses mean that these units always have to come in a set of OH. I can't have 1 oxygen and 2 hydrogens. If it says 2 hydroxides, I have 2 full sets. These come bonded together. So we would have 1 magnesium, 2 oxygens, and 2 hydrogens in this compound. Okay, so that's the total number of pieces. That's how we read the little subscripts. And the example here in your notes uses ammonia. 1 nitrogen and 3 hydrogens make up 1 molecule of ammonia. Ammonia happens to be a common name for NH3. There's only going to be a few compounds that you really need to know the common names of. Water would be one. Ammonia is another one. Pretty much everything else, we're just going to learn a set of rules for naming them, and you're going to follow those rules all the way through. This is important here, and there's stars next to it because I want you to memorize these. These 7 elements exist as something that we call diatomic molecules. So if you have them in their pure form, not in a compound, but in their pure form, they always come in sets of 2. Di, meaning 2, and atomic for atoms. So they're going to be two atoms hooked together. So if you have pure hydrogen, it's H2, pure hydrogen. If you have glucose, C6H12O2, you obviously don't have two hydrogens here, you have 12. Okay? If you have ammonia, NH3, you don't have two hydrogens here, you have 3. The only time that the hydrogen has to have the 2 for the subscript is when it's in its pure form. Same rule for oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. So my teacher taught us Hofbrinkel. That's the way that we memorized it, Hofbrinkel, Hofbrincl, Hofbrinkel. When you look at your periodic table, marking them right now might be a good thing to do. So you're going to mark on your periodic table which ones of these guys are diatomic. Periodic table is going to be really helpful when we are forming and naming compounds. And one of the first things that you might want to do, you have this key here in the middle, and I've told you have to remember which ones are diatomic. I might add a little note to myself somewhere that a little d means diatomic, and then mark the ones that are diatomic with a little d. So hydrogen's diatomic, and then over here to the right-hand side, so here's group 15, starting here, nitrogen's diatomic, oxygen in group 16 is diatomic, in group 17, fluorine, chlorine, bromine, and iodine are all diatomic. So those are your 7, those are the Hofbrinkel. Hydrogen way over here in group 1, and then this kind of upside down L over here, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Memorize that those guys are diatomic. When we have to write out full equations, it becomes super important that you know that. We also have these things called allotropes. The vocab term allotrope here means that they have alternate forms of the same element. So ozone is a really common one. Oxygen is O2. Ozone is O3. Oxygen, O2. Ozone is O3. The other one that they talk about a lot is carbon. Carbon is going to come in just plain carbon form, but we have coal, which is different. There's charcoal. There's diamond. There's graphite. They're all made with carbon. They're all made with just C's, but how they link together is going to greatly change their properties. So charcoal is very different than a diamond. You're not going to mistake the two. Graphite, the stuff that's in your pencil. These are allotropes of carbon. Carbon is unique, and that's why carbon ends up getting its own branch of chemistry, organic chemistry, which we'll talk about later. The next thing you need to know before we can form and name compounds is that atoms are neutral. Atoms with the T are neutral. So remember that. An atom is neutral. That means it has no charge at all. If an atom gains or loses electrons, they gain or lose electrons and they become something we call ions. Ions are going to be charged particles. They do this by gaining or losing electrons. Electrons are negative, so if you gain electrons, you become a negative ion. So 0 plus gaining negatively charged electrons makes you a negative ion. And then if you lose electrons, so we subtract negative electrons. So if you're 0 and you lose negative electrons, you're going to become a positive ion. So the negative ions are called anions, and the positive ions are called cations. I've also heard them referred to as cations. So if you're watching other videos and somebody says the word cations, that's just a different way of pronouncing it. I was taught it as cations, and so that's kind of the way that it stuck in my head. And I like cats, and cats are positive, so it makes sense. Sometimes we put groups of atoms together and they end up with a charge. Those are called polyatomic ions because this prefix poly means many. So poly means many. If we have many atoms hooked together and they become charged, they're called a polyatomic ion. And you need to look at reference table E. So towards the front of your reference tables, find reference table E. It looks like this. These are the polyatomic ions that we're going to use this year in chemistry. Most of them are negative. So if you look from here down, and that whole second column, they're all negative ions. So most of the polyatomic ions are negative. There's just these three at the top that are positive. This one being the most commonly used one, NH4 plus 1, is the most common positive polyatomic ion you're going to find. With these polyatomic ions, what you see in the letters and the subscript numbers are what the polyatomic ion is. So if I need to use ammonium in a compound, I'm going to write ammonium as NH4. If I need to use nitrate in a polyatomic ion, I'm going to write NO subscript 3. It has to stay with it. Okay? This superscript number, so we had subscripts, those were below the lines. These superscripts above, I tend to write the 1 in there. This reference table doesn't. They just use numbers when it's greater than 1, and they just leave it with no number at all if the charge is -1. Those are the charges. So an ammonium polyatomic ion is made of 1 nitrogen and 4 hydrogens and has a charge of +1. A dichromate polyatomic ion is made of 2 chromiums, 7 oxygens, but has a charge of -2. Be careful. Some of the names are very similar. You'll see that there's a nitrate and a nitrite very close together. There's a sulfate and a sulfite, and then this guy here, this hydrogen sulfate, throws people off because it's 3 elements in this polyatomic ion instead of just 2. So watch out for that one. Acetate looks funny, and there's 2 different ways of writing an acetate polyatomic ion. Both of them contain 2 carbons, 3 hydrogens, and 2 oxygens, and have a charge of -1. So they're the same thing. This top way is the inorganic way of writing acetate. This bottom way is going to be the organic chemist way of writing acetate. Be familiar with them. You don't have to memorize them because obviously they're here, but be familiar with the names and be familiar with the groupings and make sure you understand how we write them when we write them into a compound. We're going to put atoms and ions and polyatomic ions together to form neutral particles. The charge of your finished compound is going to be neutral. Compounds are neutral, just like atoms are neutral. If it still has a charge on it, it's not a compound, it's an ion. All right, compounds are going to get split into 2 main categories: binary compounds and ternary compounds. So we're going to go over the rules for naming binary compounds first. So we've already talked a little bit up there. Di, the prefix di means 2. The prefix bi is also another prefix that they will use to represent 2. So binary compounds, bi meaning 2, are compounds that contain 2 types of atoms. Now notice that it's 2 types of atoms and not only 2. NaCl is a very common example they use for a binary compound, but sometimes it can be confusing with the definition because there's also only 2 atoms here. But magnesium chloride is also a binary compound, but there's a total of 3 atoms, 1 magnesium atom and 2 chlorine atoms. The trick is to look for the number of capital letters. If there's 1, 2 capital letters, it's a binary compound. 1 capital M, 1 capital C, 2 capital letters means 2 types of elements. It's a binary compound. So that's your first step. Count how many types of elements there are in your compound. 2 of them, binary. We're great. Next rule is that the positive ion in a compound goes first. So if I were to split this binary compound in 2, I know that sodium has a positive charge and chlorine has a negative charge. If I split this compound in 2, magnesium has a positive charge and chlorine has a negative charge. when you look at them, eventually you're going to know what the charge of a sodium ion is, but at first you're going to have to look it up. And to do that, you're going to use your periodic table. So on your periodic table, I want you to, and let's zoom in a little bit on sodium. Right here in the upper right-hand corner, there's a little number. And on your answer key, they call that little number, if I can find there it is, the selected oxidation states. Selected oxidation states is a fancy way of saying possible charge. Oxidation state and charge are pretty much interchangeable. There's a slight difference, but for our purposes, we don't care. Carbon can make ions that are -4, +4, or +2. Those are the types of ions that carbon typically makes. Sodium only has one choice. Sodium can only be +1. Our other example used magnesium. Magnesium, over here in group 2, has a little +2 for a choice. So when magnesium makes ions, he makes ions that have a charge of +2. And then for both of those examples, I used chlorine. So if we scroll over and look at chlorine square, chlorine has a whole bunch of numbers. There's a whole list of them here. And students will say, well, how am I supposed to know which one it is? Well, when you look, chlorine's choice is -1, +1, +5, +7. Because he's coming second in that binary compound, and I said the second part has a negative charge, you only have one choice. That chlorine must have a charge of -1. So if we flip back to our lecture notes, and I look at my examples, zoom back out a little bit. Sodium has a charge of +1, and the chlorines have a charge of -1. This magnesium has a charge of +2, and chlorine has a charge of -1 each. Okay, and I set up there that compounds were going to end up with a neutral charge. Because if we look at the total compound here, so let's look at sodium chloride over here to the side. I have one sodium that has a charge of +1, and I have one chlorine that has a charge of -1. If I add the charges together, +1 and -1, that gives me a total charge of 0. The magnesium chloride, I have one piece of magnesium that has a charge of +2, and I have two pieces of chlorine that each have a charge of -1. Remember up there we said that this little subscript 2 only applies to the chlorine. So if I add these up, +2, -1, and -1, the total is going to be 0. You're going to use the concept of least common multiple to figure out how many of each atom you need to put together to make a neutral particle. Alright, so that's how we put them together. Let's look at the naming rules. Naming rules are easy. It says the first element is going to use its element name and is always your positive ion. So your positive ion, if it's an element, uses its element name. We'd go to reference table S, sodium, Na, and then magnesium, Mg. You can find them right here, sodium and magnesium. No problems. The second element, which is your negative one, gets his name changed to IDE. So Cl is chlorine. So chlorine is going to become chloride. Fluorine becomes fluoride. Oxygen becomes oxide. Nitrogen would be nitride. Iodine becomes iodide. We just change the ending to IDE. When you see this IDE ending, that's usually a tip that you're talking about a negative ion. So let's try these examples together. These compounds are all formed correctly, so we don't have to worry about the number of pieces. If we look at this one, LiCl, if I split it in half, at the second capital letter, Li, I would go to table S, find Li, it's right here, and it's lithium. So the first part of my name here is going to be lithium. The Cl is chlorine, and we just said chlorine becomes chloride, so this will be lithium chloride. Next one, HBr. Split it where the second capital letter is. H, go to reference table S. H is the very first one right here, it's hydrogen. Br is going to be farther down this list a little bit. So we keep looking. Oh, there it is way down towards the bottom here. It's element number 35. It's bromine. So I know I'm working with hydrogen and bromine. So hydrogen is the first one, so he's going to keep his element name. He's just hydrogen. And bromine is going to become bromide. So instead of bromine, I take off the INE and add IDE instead. This is hydrogen bromide. Next, split it where that second capital letter is. I have Ni and S. So again, I go to reference table S, and I look for Ni. It's right here at number 28. So that's nickel. And S at number 16 is sulfur. So I have nickel and sulfur. Since the nickel is first, it gets to keep its element name. It's just nickel. The S, sulfur, becomes sulfide. And I have nickel sulfide. Okay, last one. We have Hg and I. Hg is the first one. You're going to look that up on table S. It's mercury. So you just use the term mercury. And then I is iodine. So that will become iodide. And I have mercury iodide. The next category of compounds are ternary compounds. And ternary compounds contain 3 or more types of elements. Ternary compounds, 3 or more types of elements. So the easiest way to pick out a ternary compound is to again count capital letters. So capital K, capital C, capital O, 3 capital letters. This is a ternary compound. Capital C, lowercase a, capital S, capital O, 3 capital letters, ternary compound. Capital N, lowercase a, capital O, capital H, 3 capital letters, it's a ternary compound. Ternary compounds typically contain a polyatomic ion. So we talked about polyatomic ions, we said they're on table E. So if you see a ternary compound, the first thing you should do is go to table E and find the part on table E that's in your compound. So that first compound had a CO3 in it. So if we go back and we look, there's a capital K with a 2, and there's a CO3. That's on table S. The next one, CaSO4. When I look here, I find SO4 down here. That's sulfate. So when I look at that compound, CaSO4, that's your ternary compound. That's your polyatomic ion in your ternary compound. NaOH, again, I go to table E. I don't see anything that's Na, and then I find this OH over here. And so I go back, and the OH is my polyatomic ion. Remember, most of your polyatomic ions are negatives, so typically you're going to find the polyatomic ion in the second part of the name. Wherever you find a polyatomic ion, you use the name from table E. So this ending is going to be called carbonate. This ending will be sulfate. This ending will be hydroxide, because those are the names that we found here on table E. Hydroxide, sulfate, and carbonate. The rest of the naming is just like the binary compounds. So this first part is positive. So I look up his name on table S. A capital K is potassium. So that's going to be potassium carbonate. I look up Ca on table S. That's calcium. So this will be calcium sulfate. And Na was sodium, so this is going to be sodium hydroxide. So I got the positive ion from table S. The negative ions in these examples all happen to be polyatomic ions, so I got their names from table E. And that's it. Simple as that. So CuSO4, oh, I already know that SO4 is a polyatomic ion. This part is my polyatomic ion. NaOH we just did up there. That part is my polyatomic ion. Li2CO3, oh, I already did CO3 there. That's my polyatomic ion. Then I hit this one, and I'm like, uh-oh. I know SO4 is a polyatomic ion, but what do I do with this? These are 2 elements. I have 4 elements altogether. So if we go back and look on table E, right here, NH4 is the polyatomic ion ammonium. NH4 is the polyatomic ion ammonium. Remember I said that that's going to be the most common positive polyatomic ion that's going to show up. This compound is actually made of 2 polyatomic ions. So when I go through and name these things, copper is Cu, so this will be copper. SO4, we just said was sulfate, so copper sulfate. NaOH, we already named right there as sodium hydroxide. Li2CO3, Li is lithium. And we already looked up CO3 as being carbonate, so lithium carbonate. And this last one, I just said that NH4 was ammonium. Ammonium. And SO4 is sulfate, sulfate. What do you do if the second half isn't a polyatomic ion? The most common one that shows up a lot is this one, NH4Cl. The NH4 is your polyatomic ion, so that's ammonium. So we just still name that ammonium. And just like with the binary compounds, the Cl is chlorine, so we're going to change it to chloride because he's the negative. So this one is ammonium chloride.